Hello everyone, my name is Nasser Kimbugwe, representing my co-author, Professor Tingrui. Our title of our paper, An Efficient Privacy and Integrity Preserving Range Query Scheme over Unsorted Data. So this is the network model that we considered. So in this network model, we have these are sensor nodes, and each sensor node will send data to a storage node. So we can have different cells where each cell is sending data to its own storage node, and the sink here can send range queries to that node, to the storage node. So we note that in many queries, in many existing schemes, data collected by the sensors must be sorted, and we think that sorting it is a little bit an expensive task, that if we can come up with a solution, it will solve that the sensors from having to sort the data first. So our solution we propose is probabilistic verification neighborhood chaining model. So the good thing about this, it can work for both sorted and unsorted data. So a range query is in form AB here, whereby we want to return information that is within that range AB if there is any data. Remember, we said that each cell, all nodes send the data to the storage node M, and it is very easy to target this storage because that is where all the data is stored. So to avoid that, we need to be able, first of all, to protect and preserve the privacy of the data that is collected from the nodes. It's not wise to attack individual nodes because it has very little information, but when you attack the storage node, there you have access to a lot of information. So our aim here, we are targeting working with M. So and the second thing is we must be able to verify the integrity of the range query results that are received from M by the sink, as we saw in our network model, this one. So the sink sends the query and then receives the feedback. So we must be able to verify that, one, that the data returned satisfies the range query. If we say we want data between 10 and 20, then all the information returned must be between 10 and 20. 2, all the results returned are valid and not just forged. And 3, that some data is not dropped. So the adversary can do a lot of all these if it attacks our M. So related work, because of time, we refer the listeners to our full paper for a full literature review. These are the notations that we used in our paper. So we shall refer to these notations. So our model, we have a model that works for sorted data, but we ignore that in this presentation. Viewers can refer to the full paper. So we are looking at our PvNC model, and in our PvNC model, each element is linked with L elements. And those L elements, L over 2 are on both sides. So if we choose 4 elements, so 2 elements must be on the left and other 2 elements on the right of data element D1. So Now, if any side of D1 has less elements, then and the other has more elements, so L elements on D1 side with less elements are chained with D1, and the remainder are chained from the side with more elements. So for example, if you have 7 elements to chain together, so 3 will be chained on the left, 4 on the left, and then 3 on the right. So in other words, our PVC model, to summarize, is like this. So we have a data element Di, and it is joined with some elements on the left, which elements are L over 2, and also some other elements on the right. So these ones are to be used in verifying the query. So for now, if we use live examples, so if we have a 6 and our element is 4, so we are going to concatenate a 6 with these elements, okay, and then the 3 will also be concatenated with some elements on the left and the right, and so on. So it is challenging if this information is not encrypted. So to be able to encrypt this information, we apply what we call the 0-1 encoding mechanism, as we used it with ABC. ABC is in the full paper. So here, after linking the information, we apply a key, so which we call KIT, that is a key for a particular data, for a particular sensor I at a particular time T. So we use the encoding model, and that encoding model can help us to verify that the data is greater or less than the other some data without necessarily using the greater than symbols. And the full explanation of 0-1 encoding is also in the full paper. So after getting the 0-1 encoding, we use what we call a unique, we get a unique number by adopting what we call enumeration function mechanism. It is also in our reference, in reference 4 and 7. And then after that, we pass that enumerated number into a HMSC function to be able to secure that data. So finally, this is what we send. This is what the sensor will send to the storage node. It will send the sensor ID, the time, and of course the PVC number, and then the enumerated coded numbers, which will be used to verify the range query. So the range query submission. So if you want to query, so the sync will send to M this. It will get the encoded numbers of A and B and send to the sync to the storage node. So the storage node, upon receiving this, will have to look up the encrypted PVC data that satisfy the range query, and then returns that data. So, and all that data which qualifies must follow this. Okay. So if the encrypted, the encoding enumerated numbers of A union B is equal to, is empty, so D1, this is now the number that was sent already by the sensors, that is already in M. And then, so all the data that satisfy this condition, those are the data that are required. And then our M will send this to the sink responding. So the sink, upon receiving the data, will again decrypt it and then compare it to see if no data was dropped or data is not forged, and so on. So our experimental results, we use these parameters. They are also in the full paper. And then we saw that this is our PVC detection of dropped data in case the storage node drops some data. The more data that is dropped, the easier it is to detect that some data was dropped. And then this looks at the false positives. Sometimes data that is not required is sent, and we compare with existing schemes about no, this is the communication cost. We see that our model communication cost is relatively lower than some of the existing schemes. And this one is the one looking at the false positives. So our PVC model returns the more the number of networks elements returned, the lower the false positives that are returned. And then in our conclusion, yes, we make two contributions. We propose a model called FDC that is in full paper, and another one, PvNC, whose power consumption is lower than the existing. So we also observe that sorting data before it is sent to the storage node is quite extensive work, and if it can be avoided, that would be good. So these are the references. Some are in external, in the full paper. So thank you for watching. God bless you.